So welcome everybody. My name is Richard Holdaway. I'm director of the space part of STFC and RAL here on site. So it's my pleasure to welcome you all for what really promises to be an exciting day, because boy has this place changed over the last 10 years in terms of its remit from government. And the way it's changed is exactly summed up by the sort of things you folks are doing today, which is taking the impact of the innovation that we develop here and spinning it out into other areas, and in particular, of course, to the medical program. Right, okay, so addressing the needs of healthcare, and one of the things we do on this campus, I've got to remember to keep standing in front of this thing. One of the things we do a lot of in this campus, as I said, is to take our technology that we're developing for our own programs and spin it out into other places. So what are the other programs here? Well, this is the campus itself. The big donut-shaped building that many of you, but not all of you, will be familiar with is Diamond, the world's first third-generation X-ray synchrotron. And there's a connection between that and lasers. We've got the world's most intense laser system in a building about 150 yards from here, together with ISIS, which is the world's most powerful source of pulse neutrons. And all three of those facilities are very large, science-led, but technology-enabled facilities, funded primarily by government, but used by industry, as well as by our own researchers here, as well as by universities. And the whole concept for those three facilities, in different ways, is developing new drugs, looking at smart materials, looking at new materials for aerospace, for the Formula One program, materials for almost anything in life. And a number of you in this room now, I'm sure, are already either users of the facilities directly or users of the research that comes out of that. We also have, because those facilities always, of course, provide so much data, we've got supercomputing on the campus. We've got RAL Space, which I have the pleasure and honor of running. And I'll just say a couple more words about that in a moment. And then just outside the campus, across the gate, we've got the European Space Agency, and we've got the Space Applications Catapult. Both of those are here on the campus because of the links they can get to all of the other departments here that you see on the slide. And ESA in particular is here because it wants to be able to pick up the science-led work that we do as well as the technology we do. The catapults, as you probably know, are set up by government to bring together industry, to bring together academia, to bring together research institutes like ours, and make sure that the whole is greater than the sum of the parts. And so it is this same story of innovation and actually at the end of the day, job creation, which ultimately is what government wants. Just going to give you one example before I finish. This is a few years old now, but it's a very good example of the kind of stuff that we do in this particular instance on the space program. So there on the left-hand side, you've got terahertz waveguides that we used for many years for both the radio astronomy program and for our planetary program. We developed that stuff, and this operates at typically 2 or 3 terahertz, which also has applications in the medical field. But it was a 50,000K grant we got. And one of the most well-known uses of that technology was on the Huygens probe from the Cassini mission, where we were looking at the molecular composition of the atmosphere of Titan as we came down. We also use it for the radio astronomy program. But it's very interesting technology because what you can do is you can find a particular molecule of a particular type remotely, which of course is what part of today is about, and when you're looking at several billion molecules and you're looking for just one. And this system can do that. So we took an innovative approach to say, well, if we can do that in space and we can do it remotely, can we do it terrestrially? And the answer is yes, we can. And here's somebody that's not had one of this morning's bacon butties, which, by the way, if you haven't had one, they are really, really good. And any conference that starts the day with a bacon butty's got to be on the right lines. That's somebody there with plastic explosives underneath their clothes. And of course, one of the things that we need to be able to, we globally need to be able to do, is to identify nasty stuff like plastic explosives that are under people's clothes and do it remotely. I really don't want to be standing next to Googs here when he's got plastic explosives and he's ready to explode himself, because I'm going to come off pretty badly as well. But I'd like to know if he had got that stuff under his clothes when he's 100 yards away coming towards me. And that's the sort of thing that system can do. And there's one of the cameras that were developed here out of the space program, doing this kind of stuff. There's one of the cameras there at Heathrow, We spun that business out. It's a multi-million-pound business now down at Milton Park, a few miles away. But it's this type of example of the innovative technology that we're able to do on this campus, and that's just in one department. So when you're having your 10 o'clock love-in today, meeting partners, looking around at the different displays and so on, and looking for ideas, be creative in the questions you ask as well as the answers you expect back, because this was totally serendipitous. And we got it, we were able to do it just because somebody said, hang on a minute, if we take that technology looking in that direction and we look in a completely different direction, okay, I mean, I'm talking lateral thinking, not literally looking in opposite directions, you can come up with all sorts of innovative things, which you all know very, very well, but there are always lots more things that we can do. So thank you very much indeed for coming.